Hello everyone and welcome to the second video of the third lecture of the course on metric spaces. In the last video we defined a metric on the sphere using the metric on the space. In this video we will define another metric on the sphere using arc length. So first of all, let us recall how we compute the length of an arc. So I will draw a circle like this one and I will put it inside the plane. So I will draw the x-axis and the y-axis, respectively the y and the x-axis. Then what I want to do is that I want to take a point P on this circle and draw the angular sector given by the x-axis and the segment connecting the origin O with the point P. The question is how long is the arc going from P to the point in which the circle intersects the x-axis. Let's say that the circle has radius 1, so this point is exactly the point 1, 0. And the question is how long is the red arc? Well, we know that if we measure angles in radians and we assume that the angle formed by the segment OP and the x-axis is equal to alpha radians, then the length of the red arc, which I will call L, is given exactly by alpha. So the length of L is alpha when alpha is measured in radians. So for example, if alpha is equal to pi divided by 2, which means we're taking the point P here, then the length of L is exactly pi divided by 2. And if we take the full circle, which means we take alpha equal to 2 pi, then the length of L is 2 pi, which is exactly the length of the circle of radius 1. Now, the question we should ask is what happens if the radius is not 1 anymore? Well, if the radius is r, then the length of L, individuated once again by alpha, is given by alpha times r. Now, we want to use arc length to define another distance on the sphere. So let us draw the sphere. We have to draw three axes: the z-axis, the x-axis, and the y-axis. Then we draw the sphere, and we want to give a way to measure distances between points on the sphere. So let us recall that our sphere has radius 1, which means that the intersections with the three axes of the sphere are equal to 1, 0, 0, 0, 1, 0, and 0, 0, 1. This will be important later because it will mean that we have to use the formula for arc length for a circle of radius 1. So, as I said, our aim is to define a distance on the sphere using what we just recalled. So let us fix 2 points, P and Q, on the sphere. What we want to do is we want to draw the maximal circle, so the equator, which goes through P and Q. So let me draw this maximal circle, which is more or less this one. Then what we want to do is to use this maximal circle to compute the distance between P and Q. Basically, what we want to convince ourselves is that even if we are in 3 dimensions, everything will actually take place in 2 dimensions. What I mean by this is that if we consider the maximal circle on which P and Q lie, this is given by intersecting our sphere with a plane that contains P and Q and which is chosen in the correct way. Therefore, even if we started in 3 dimensions, actually we can work in 2 dimensions on a specified plane, which in our case is the blue one I've just drawn. Then what we want to do is we want to pass to this 2-dimensional picture in which I will draw 2 axes to whom I won't give names because we would have to give them names respect to the plane we chose. And in here I can draw the circle on which I've taken the points P and Q. And they are here, P and Q. Then I can consider the angular sector identified by these 2 points and take the angle alpha that defines this angular sector. And then I will say that the distance between P and Q is exactly equal to this angle alpha. Notice that I'm taking the smaller angular sector, by which I mean I'm taking the shortest arc on the red circle connecting P and Q. And we have to do this if we want to be sure that the distance we define is indeed a distance. So let us recap a little bit what we've done. We said that to compute the distance between 2 points P and Q on the sphere, we have to take the maximal circle going through P and Q, and then as this circle can be seen as the intersection of a plane with the sphere, we draw this circle in that plane and we consider the angular sector individuated by P and Q, the one with the shortest arc, and we define the distance between P and Q exactly as the length of the shortest arc connecting P and Q on the maximal circle. Let's see an example to make things a little bit clearer. We'll take the point P to be 1, 0, 0, and the point Q to be 0, 1, 0. Then the maximal circle on which P and Q lie is an equator, and it can be taken to be the one individuated by the plane Z equals 0. It is exactly the one I'm highlighting now. It's this yellow one, the maximal circle we will take to compute the distance between P and Q. Then, if we draw the axis and we draw the circle, we see that the points P and Q are respectively on the x-axis and the y-axis, because in this case they are exactly on the x-axis and the y-axis in the picture when I take the plane z equals 0, and the angle is given by pi divided by 2. So the distance between P and Q, in the way we've just defined it, is given by pi divided by 2. In the exercises, you will have the chance to look at some other examples of distances computed using this distance, and in the next video we will make a comparison between the distance we've just defined using arc length and the distance we defined in the previous video, inheriting it from the space. So see you in the next video.